Unit 4 will cover solutions. Um, so solutions. So define terms associated with solutions is what we're going to address first. Solutions are defined as solute plus solvent. And you might think, I don't know what solutions are. I don't deal with them on a daily basis. But if you've ever had Kool-Aid, for instance, that is a solution. So with Kool-Aid, you have this solution. And what is the solute? Well, it depends on the type of Kool-Aid that you make. Um, I am a Kool-Aid purist. I feel that you have to have at least a cup or two of sugar to make your Kool-Aid um, legitimate, right? The sugar-free Kool-Aid is not really Kool-Aid. Um, so the solute in Kool-Aid would be the packet. So with the little pitcher guy. Um, and then your solvent would be water. Now, you can have more than one solute in a solution. So if you're using the sugar-free Kool-Aid, then you don't need to add anything else besides the packet. But if you're using the Kool-Aid that requires sugar, then you would include that as your solute as well. Um, so a lot of this unit is going to cover concentrations and dilutions, and in whatever chemistry course you go into, whether it's General Chemistry 1 or Chem 122, Principles of Chemistry, you will spend a whole unit on solutions. And in my opinion, for both of these courses, it's a pretty challenging unit. Um, so keep that in mind when you're working through this packet. Um, if it's more challenging to you, it should be. We've been kind of ramping up all semester trying to get you ready for your next chemistry class. So be prepared to be challenged, and you might have to put a little bit more work in. You might have to do more practice problems, maybe get some extra help. It does require more work. So, but I'm not trying to say that, I'm not trying to be discouraging, just realistic. Okay, so let's talk about water. Um, So remember, water is H2O, and the Lewis structure for water looks like so. Um, remember that water is polar. It's polar because it has a polar covalent bond. And it is also unsymmetrical. It's bent. So because it's polar, we can use these little symbols, the little partial negative, partial positive, partial positive. So it turns out that water has a special type of bonding that it displays. It's called hydrogen bonding. And hydrogen bonding is not this bond here. I'll show you what hydrogen bonding is. So hydrogen bonding is the attraction of a hydrogen attached to an electronegative atom, O, N, or F, and another nearby oxygen, nitrogen, or fluorine atom. I'll write this down for you in a second. But this red bond that I'm drawing here, this is hydrogen bonding. A lot of students mistakenly think that hydrogen bonding takes place between this oxygen and hydrogen, which it doesn't. It's within, it takes place with another molecule. So hydrogen bonding gives rise to a high boiling point in water. So this means that water likes itself so much that it doesn't want to let go, right? You have these liquid water molecules, and they're all close. They have their hydrogen bonding. They got this whole network. They don't want to go from liquid to gas. It takes a lot of energy. So that's why water has such a high boiling point. The other thing that hydrogen bonding gives rise to is a high surface tension. So think of those water bugs that can walk on water. They're taking advantage of water's hydrogen bonding capabilities. Um, so uh, being able to balance a needle on water, that's another example of this high surface tension. Okay, so hydrogen bonding is the attraction of a hydrogen attached to an electronegative atom, and that electronegative atom must be oxygen, nitrogen, or fluorine, and another nearby oxygen, nitrogen, or fluorine atom. Okay, so I have a question for you. Um, which of the following can participate in hydrogen bonding? Okay, so this is an example of what you could expect to see on the final. Okay, so which of the following can participate in hydrogen bonding? And remember, this is not the bond between the oxygen and the hydrogen. It's the bond that isn't explicitly written, that is caused by this polarity of water. So a partial positive on hydrogen is attracted to the partial negative on a nearby oxygen. So in order to answer this question here, which of the following can participate in hydrogen bonding, you're going to need to have a hydrogen, and then you're going to need to have an oxygen, nitrogen, or fluorine. So you can eliminate A. It does have hydrogen, but it doesn't have oxygen, nitrogen, or fluorine. You can eliminate B because it doesn't have a hydrogen. C has a hydrogen and it has a nitrogen, so that satisfies the criteria, so yes. D, H2S, if it were anything other than S, but it's not, so that you can eliminate if it was O, N, or F, where S was, but it's not. And then E, H, F, yes, that satisfies the hydrogen bonding requirement. All right, so I know I went over this at the top of the paper, but it never hurts to repeat this. A solution is solute plus solvent, and I'll elaborate a little bit more. The solute is the smaller amount. It usually changes phase. It's supposed to be an M, abbreviation for amount. So usually changes phase. So I mean, it usually goes from solid to aqueous. That would be a phase change. The solvent is in the larger amount and often is water. Okay. So we're going to go on to the next page and talk about what happens when things dissolve. So when you get solutions or when solutions are created. So like dissolves like, polar dissolves polar. Nonpolar dissolves nonpolar. Okay, so that's why water and alcohol are soluble together. Um, Oil and water do not mix because oil is nonpolar, water is polar. So um, let's look at what happens when we have an ionic compound that dissolves in water. So remember, an ionic compound is a metal to a nonmetal or any polyatomic ion. And water, of course, is H2O. All right, so we have, let's say, NaCl. So when you break NaCl up into its ions, it's Na plus, Cl minus. Now we know that water is polar and it has the partial positive and the partial negative because of that electronegativity difference and the shape. So it's polar covalent and it's unsymmetrical, so we know that it's going to be polar. Now, the way that this water molecule aligns itself around these ions is unique. This water, these hydrogens, are not going to be attracted to that cation. Instead, oxygen would be attracted to that. So water will align itself around sodium ion like so, because the oxygens like being around that negative, the positive charge, because the negative on their oxygen is attracted to that. So you hear opposites attract, and that's certainly the case here. So these little sigma negatives, that's why they align that way. Now, when you get to chloride, the negatives aren't going to align around chloride, but the positives would align around chloride. So you end up with water molecules like so, where the hydrogens are pointing inward. And I'm not asking you to predict how many water molecules surround each ion. It actually varies, but we don't get into it in this course. But you can see why it aligns itself this way. So you have a partial positive, partial positive, partial positive, partial positive. That's aligning around that chloride. So this is called hydration. Okay. Now I have a practice problem for you. Identify the solute and the solvent in each solution composed of the following. So I have 50 grams of silver and 4 grams of mercury. So the larger quantity is going to be the solvent. Smaller quantity is going to be the solute. So mercury will be the solute, silver will be the solvent. And B, 100 milliliters of water, 5 grams of sugar. This will be your solvent. Sounds like your Kool-Aid maybe. And then your solute. It would probably be more sugar. More like 100 grams of water. Or 100 grams of sugar to 100 grams of water. Okay, this last one, iodine and alcohol. Even though these are different units, you can see that there's a lot less iodine. So this is the solute, and this is the solvent. Okay, so we're continuing on talking about solutions, and I want to add this. I didn't include this part in your notes, and I want to add this. So let's say the sodium chloride solubility at 25 degrees Celsius is 35 grams of NaCl. Sorry, I can't. There, NaCl per 100 grams of water. Okay. So we're going to use this to refer to. Sometimes you will hear solutions described as saturated, unsaturated, or supersaturated. So let's go over these definitions. So a saturated solution. This is a solution that holds the maximum amount of the solute under the solution conditions. So in this example, the amount would be 35 grams of NaCl per 100 grams of water. So you're never going to be able to get more sodium chloride into that solution. So 35 grams gets into that solution. Now, if I say I take 40 grams of sodium chloride, I weigh it up, and I put that in 100 grams of water, you're going to have 35 grams that's dissolved in water that you can't see, and then you're going to have 5 grams that's at the bottom, so that you see as just the salt granules. Okay, so let's go on to the next one. Let's see, unsaturated solution. Holds less than the maximum amount of solute. Okay, so in this case, an example would be, say, 15 grams of NaCl per 100 grams of water. So I could still dissolve 20 more grams of sodium chloride. So it's unsaturated. Can still get more dissolved. All right, and lastly, we have the supersaturated solution. This holds more than the normal maximum amount of solute. So it's unstable. Um, so I don't know if there are any sweet tea drinkers out there. So you like to have your tea really, really sweetened. Well, what's a trick that you can get more sugar in? You can heat it up, right? So if you heat it up, you're getting more sugar into your tea than you would at, say, room temperature or iced tea. So an example of this for the sodium chloride example would be 50 grams of NaCl per 100 grams of water. So that exceeds the solubility that you were given. Okay. And then the last part of this lecture that I'm going to cover is um, describe the solution process for electrolytes and non-electrolytes in water. I am going to eliminate this weak electrolytes part. We do not need to cover that right now. Um, so whenever I introduce this concept of electrolytes, uh, I always use this example. You know, if you have um, two bathtubs, and one is a strong electrolyte and one is a non-electrolyte, and the electrolyte means that it would conduct electricity. I say, you know, which bathtub would you rather drop your hairdryer in? The non-electrolyte bathtub or the strong electrolyte bathtub? And students inevitably will say the non-electrolyte bathtub because electricity would not be conducted. So um, we have electrolytes all around us. We drink them often. When you go to the hospital and you need to get an IV therapy, you get electrolyte replenishment. So depending on what type of IV solution you're being administered, but um, Gatorade is an electrolyte replenishment therapy. So if you're ever in kind of a funny grocery store, I think I always chuckled at this. There's one grocery store I would go to that you know it would, on the aisle heading it would say soda, water, and then it said electrolyte replenishment therapy. It's like, oh, they're talking about Gatorade. So, or Pedialyte or anything along those lines, Powerade or whatever brand you prefer. But okay, so strong electrolytes conduct electricity through ions. So they are ionic compounds. And I want to specify they are soluble ionic compounds. So remember those solubility rules that you memorized? Yeah, the ones that are insoluble, those are not going to be strong electrolytes because they do not dissolve. They will not ionize. So strong electrolytes um, are soluble ionic compounds. An example will be sodium chloride. And a lot of students say, why does it say S? That means it's insoluble. This is when it's in the bottle. When you buy sodium chloride at the store, it's solid, right? You know, Morton salt, the little girl with the umbrella on it. Um, so when you take solid sodium chloride and you combine it with water, what happens? It ionizes and it dissolves. So it goes like this. And I remember my solubility rules. All group 1 salts are soluble. Um, all chlorides are soluble except for those few. AgCl, PbCl2. Okay, so, and then mercury chloride too. So when you have an ionic compound that is soluble in water, it's going to form 100% ions. And these ions are going to conduct electricity. And that's why you do not want to drop your hairdryer in a strong electrolyte. So I'm making you work for this next one, solid aluminum nitrate. I want you to try to write the formula for aluminum nitrate. So what is nitrate again? If you're a little rusty on your polyatomic ions, I know it's been a little while since we've had them, be sure to review them before the final. So solid aluminum nitrate. So aluminum is 3 plus, nitrate is NO3 minus 1. Do the cross, the drop, you get AlNO3, 3 solid. When you put that in water, because it is soluble, because all nitrates are soluble, you're going to get Al3 plus aqueous plus NO3 minus aqueous. I'm going to put it's not balanced right now. I have 1 aluminum, 1 nitrate, 3 nitrates, so I need to put a 3 there. Okay, so we learned what a strong electrolyte is. Now, the opposite of a strong electrolyte would be a non-electrolyte. So, non-electrolytes do not conduct electricity. They are usually molecular solids. What do I mean when I say molecular? They bond via covalent bonds. So covalent bonding, that takes place with nonmetals to nonmetals. Remember, those are the ones that share electrons. They do not give up electrons, transfer electrons. So a classic example would be sugar. So sugar does not ionize. This is carbon's a nonmetal, hydrogen's a nonmetal, oxygen's a nonmetal. So this participates in covalent bonding, and it's not going to ionize, so you end up with C6H12O6. And the only thing that changes is this goes from solid to aqueous. So notice, because there's no charge, no electricity is conducted. Therefore, no electricity conducted. So now back to the hairdryer example. If you had a choice to drop your hairdryer in a solution that didn't conduct electricity, that would be ideal, as opposed to one that conducts a lot of electricity. Okay, so that will conclude our lecture for this portion of Unit 4. We have some more lectures after this that will get more into concentrations and problem solving. But go ahead and work the homework problems for this section, and I'll see you next time.